everybody. Today we are going to start a new topic of discussion in which we are going to look at the fundamentals of nucleation of crystallization. We have already looked in the last lectures about polymorphism, the fact that polymorphism is a very important area of interest. We have also looked at the existence of anisotropic and monotropic polymorphs, and in case of anisotropic polymorphs we know that there is a solid to solid phase transition before melting, whereas in case of monotropic polymorphs, each polymorph has got its independent set of existence at temperatures below the melting point of one form. Now we are going to look at the fundamentals of nucleation, where we have a compound of interest which we would like to crystallize, and it is to be realized that the process of crystallization essentially involves large number of molecules which are actually floating around in solution, and we see that there are concentration fluctuations in the system. There are also thermal fluctuations in the system. So the molecules are randomly moving around in different directions, and they are also colliding with each other, and this is now a process by which we would like to facilitate crystallization by different techniques. One such technique is lowering the temperature of the solution, by which we will allow the kinetic motion to be reduced, such that the molecules can now come close to each other. Intermolecular interactions exist between the molecules now, and they can now start creating a small cluster of molecules, and then this cluster of molecules should tend to get ordered, and finally they will form the crystal. So there are different steps here. First is the formation of a cluster which has got the required number of molecules which will create the essential nuclei, and these nuclei will further grow, and then that will give rise to the crystal. And to achieve this crystal formation, there is a condition which is required, that is known as supersaturation. If we have undersaturated solutions, then crystallization does not proceed. If we have very high degree of saturation, then there is precipitation of the compound. So we need to actually control or modulate the levels of saturation, preferably have low levels of supersaturation, such that we can facilitate the process of crystallization. Now this can be understood very clearly looking at this particular diagram, where we have got concentration is a function of temperature. We have this as one zone and we have another zone, and this is the metastable zone width. This is the equilibrium solubility curve, and this is the unsaturated solution which is stable. Supersaturated solution is metastable. This is the labile excuse me, region which is unstable. So what in case of the unsaturated solution, the solubility is less. Equilibrium thermodynamic solubility. So the goal then is to increase the degree of supersaturation such that the concentration of the solute exceeds the equilibrium solubility of the system, such that it enters into the supersaturated region. So now we are going to lower the temperature of the system. On lowering the temperature of the system, because we know that in unsaturated solution the crystallization is not going to take place, it is only when we reach the supersaturated region that or the metastable region that the process of crystallization can proceed. So, and this can be achieved by, so the first step is the unsaturated solution, and then the second step is to increase the degree of saturation such that the concentration of the solute is greater than the equilibrium solubility, that is supersaturated. And for this there are different methods. For example, we can lower the temperature of the system, evaporation of the solvent, because that increases the effective concentration of the solute, and evaporation of the solvent can be done, or you can add an anti-solvent, which is a miscible solvent, but in which the solute has significantly less solubility. So the anti-solvent addition can take care of the process of increasing the degree of saturation. And the moment you are entering into the supersaturated region from the unsaturated region, it is not that crystallization will immediately proceed. There is a hysteresis or a time lag associated with the process of the nucleation of the crystal, and the nucleation of the crystal is supposed to give me small size clusters, which are also referred to as nucleation aggregates. Okay, and it is these nucleation aggregates which are actually going to grow further and give you the crystal. And the nucleation, once the nucleation happens, and only when the nucleation has reached a stage when the critical size of the nucleus has been reached, after which the growth mechanism takes place. Below the critical size, growth will not take place, and there is also a tendency for the molecules in the nucleation cluster to redissolve back into the bulk solution. So you have the possibilities of formation of the nucleus and also dissolution of the molecules or the particles back into the solution, and these processes are controlled by local fluctuations in the concentration and also the fluctuations in the thermal energy of the system. So the internal dynamics are extremely important in controlling the processes of nucleation, and achieving the critical size of the nucleus is extremely important, before which no new growth will take place. So this process of crystallization on reaching the supersaturated region does not immediately take place, and so there is a hysteresis or time lag associated with nucleation. Hence, the supersaturated solution can exist in a metastable state in which it does not spontaneously crystallize. So now how do we achieve crystallization then? Because we have now reached the metastable zone, the supersaturated zone, and the range over which this metastable zone exists is given by this particular arrows. And now on further, if you lower the temperature, you can see that the system now moves into the labile zone. So, once the system moves into the labile zone, it is now an unstable zone, and it is at this stage that the process of nucleation and crystallization begins. So, now increasing the saturation further, the system moves into the labile zone, which is also the unstable zone, and it is here where the process of primary nucleation in quotes and subsequent crystallization begins. So, once you have reached the labile zone, or I would say extremely high levels of supersaturation, that is when the process of primary nucleation and crystallization begins. So, the key to getting good quality crystals in a crystallization experiment is to actually approach the labile zone first as slow as possible, so that you have got limited nucleation which takes place. So, it is always recommended that we do not want a large number of small sized nuclei to grow. Rather, what we would want is a very controlled process where only a few nuclei grow, and then these nuclei become bigger and bigger, and the crystallization proceeds in a facile way. So, sometimes what we do, we also add seeds to the solution when it is in a supersaturated state, and that can possibly now initiate the process of nucleation and growth. But that is referred to as a heteronucleation process, where you have added a seed in comparison to that of a homogeneous solution, where the crystallization is taking place from the bulk solution. So, we have homogeneous as well as heterogeneous nucleation. We are not here considering the addition of external seeds or any heteronucleation processes, but we would like to grow good quality crystals. To obtain good quality crystals via the process of homogeneous nucleation, the key is to approach the labile zone as slowly as possible. As slowly as possible. This results in the formation of small number of nuclei which can now possibly further grow into larger size crystals. So, as this process now further goes, now we can write here. So, once you have initiated the formation of a small number of nuclei, then we can say that the crystallization proceeds. And the concentration of the solute decreases, and what happens? The system moves away from the labile zone and subsequent growth takes place. On a relatively few nuclei which are produced. So, this we have now realized is the essence or the basis of doing the nucleation, of understanding the process of nucleation, controlling nucleation and the subsequent growth processes. And once you have the required number of the small number of nuclei, then large size crystals can be produced, and once large size crystals are obtained, this process will go on till the process of till the process of crystallization is complete. Say you have added a solvent, the complete evaporation of the solvent takes place, and now you can take these crystals for doing further experiments. So what we would like to do is to control the number of the small size nuclei which are formed, and not have uncontrolled nucleation where we have large number of small size crystals. So the important thing is to have a relatively low degree of supersaturation. This is what is essential. A relatively low degree of supersaturation is necessary because this results in high quality crystals, and these crystals will also have much reduced defects. So we do not want very high levels of supersaturation because precipitation can take place, and the necessary crystallinity which is required will not be there in the crystals. You cannot have undersaturated solutions, because then the process of nucleation doesn't start. What you need actually is a metastable zone which actually corresponds to tuning the levels of supersaturation, such that the moment you cross the supersaturation region and reach the labile region, crystallization process begins. It is controlled, the process of formation of nuclei is slow, and subsequent growth can also take place. So what is very important is the formation of a nucleus of the right size. Now in this regard, it has to be kept in mind that when the process of nucleation takes place, there is a new interface which is being created, because you have a solution till now, but now you are creating a solid. So there is a solid liquid interface, and the nucleation will only be a facile process when the free energy which is necessary to form this surface will overcome the energy which is spent in creating the surface. So there is overall we would like to form the crystal. So there is a free energy change associated with the creation of a large amount of matter, that is the volume. So if the free energy of creation of this bulk crystalline material exceeds that exceeds the energy which is necessary to create the solid liquid interface, then this process of nucleation will happen in a facile way. So we need to write down this statement. This is a very important statement because there are two important factors here. You need to create a new solid solution interface and the free energy available to form this interface depends on the supersaturation of the solution, as we have already seen, and the nuclei will exist if the free energy required to create the interface, or the penalty which has to be given in terms of the free energy to create the interface is recovered from the free energy gain in forming the bulk crystalline material. So, the free energy which is available to form this interface, that is the solid solution interface, it depends upon the degree of depends on the supersaturation, and the nuclei will exist if the free energy required to create the interface is recovered from the free energy gain in forming the bulk crystalline material. So, in this regard there are different models which have been proposed, and one is the classical nucleation theory, and the other one is the non-classical nucleation theory. So, in the case of the classical nucleation theory, we have got these ions, atoms or molecules which are floating in solution. And what happens is that these come close to each other to form a nucleus. This is an ordered array. So, this is the nucleus of the right size, and now this nucleus can grow in 3 different directions and can give you the crystal. So, it can give you the crystal. This is referred to as the classical nucleation theory, whereas in the non-classical nucleation theory, it actually follows a 2-step pathway. It actually follows a 2-step pathway, wherein we have got first random collection of particles which are actually containing the atoms or the molecules which are floating around in the solution. Initially, they form a dense nanocluster, and from this nanocluster what emerges is a nucleus. So, we see here that we have this nucleus which is formed out of this nanocluster, which is actually a dense nanocluster, and once the nuclei has been formed, then finally the nuclei has been formed, that is the process of nucleation has takes place, then the growth can happen leading to the formation of the crystal. Of the desired morphology, shape and size. So, there are 2 steps. There is first a process where these clusters actually come really close to each other and forms a dense aggregate, and from this dense aggregate the nuclei is generated, which can now further grow to give you the final crystal. So, there are 2 steps. This is the first step where you have the formation of a dense nanocluster, and the second is the formation of the nuclei from the dense nanocluster, followed by the growth mechanism to give you the crystal. And there are now many experimental techniques which have been developed to validate the non-classical nucleation theory, and which is more of a non-equilibrium process in comparison to the classical nucleation theory, which is more of a equilibrium process. And it has also been observed using different microscopic techniques that the formation of polymorphs actually happens from this aggregation of molecules to form the dense nanocluster, and then this dense nanocluster can now form different kind of nucleation aggregates which can actually crystallize as different polymorphs, say P1 and P2. And this is actually the onset of, or the reason for the occurrence of concomitant polymorphism, because now in the same crystallization container we have two different sets of nuclei which can now grow in different ways to give you a set of almost near eco-energetic polymorphs P1 and P2. And sometimes it is also observed that these dense nanoclusters which are formed can also disaggregate in solution. They need not aggregate. There are concentration fluctuations where this dense nanocluster can again go back into the solutions because of the thermal fluctuations, because of the concentration fluctuations, and then they can again reassemble together and maybe in a different way, and that can now crystallize to give you the other polymorph. So sometimes what happens is that because the concentration fluctuations and the temperature fluctuations are there, these dense aggregates or the initial set of nuclei which are formed can now again redissolve back in the solution, and they can again reaggregate, and now they form another crystal which can now convert into the different phase. So there are a lot of interesting things which happen, and it is not necessarily the initially formed cluster or the aggregate which will give rise to a particular structure. These dynamical processes are continuously happening in solution as well. And this particular thing has been observed in case of one particular example I would like to give you, that this two-step nucleation model, the two-step nucleation model has been investigated in the crystallization of olanzapine drug, OZPN. And what has been shown is that you have got, you start with the crystals you start with these kind of crystalline surfaces, okay, and you will see that there is the formation of nano droplets that are concentrated at the steps. So you have got these nano droplets that are concentrated at the steps which correspond to the surface of the crystalline form of olanzapine, and now these it is these nano droplets which are initially formed that now get converted into the corresponding crystalline form. So it is not that the entire solution simultaneously crystallizes into and forms the three-dimensional crystal, but it is actually the process where you have the formation of these dense aggregates or the dense nanoclusters, which is reflected in these nano droplets which are happening at the steps, because it is the steps, it is a step region where the further growth has to take place. So these nanoclusters come and get deposited, and further growth can now take place, and this droplets will now lead to the final of the crystal structure of olanzapine, which is the OZPNDD, and that is the dihydrate form, and that is the dihydrate form of olanzapine. So we are able to get this particular structure, and this we are able to do because we are starting with OZPN form 1 lattice. So we have the OZPN form 1 lattice now, and that converts into the dihydrate OZPNDD. However, if you actually stir the solution, if you continuously stir the solution, then these droplets will go into the solution and then crystallize as the kinetic dihydrate of OZPN, which we call as OZPNDB. So, we started with the form 1. We can either get the dihydrate, one particular polymorph because of the crystallization using the two-step nucleation model, or we can stir the solution where the droplets now go into the bulk and then crystallize as a kinetic dihydrate of OZBN DB. So, this has been possible to study using AFM, that is atomic force microscopy. Then people have also used electron microscopy to get evidence for the formation of an amorphous phase. That is, we call this the pre-nucleation aggregate, something which is not even nucleated, but there is some evidence of the formation of some kind of clustering of particles which do not have the necessary ordering, but are essentially amorphous in nature, and this has been observed, that is the indication of an amorphous phase during the process of crystallization of organic compounds. So, microscopic techniques have been very useful to understand and validate the two-step nucleation model. Now, in the next lecture, we will look at a little bit more into the role of, I mentioned to you, the different factors. So, we have got a free energy requirement of creation of the interface, that is the solid solution interface, and we also have the free energy gain, which is accompanying the formation of large volume of the crystalline material, and a competition between these two factors is what drives the process of nucleation and subsequent growth, and we will look into some of these processes in more detail in the next class. Thank you.